All right, thank you for tuning in. This is our new video for tonight, or this first one. Today we're going to be talking about motion graphs. Motion graphs are another representation of motion, like the motion diagrams that we did yesterday. What motion diagrams do is they're actually very easy to look at and figure out what's happening. But motion diagrams have some limits that they can only show a fairly limited range of what's happening. Like they can show objects that are speeding up and slowing down, but as soon as it starts switching directions and things, the dots start overlapping and start getting very messy. So motion graphs can give you guys more information at the cost of being a little bit harder to interpret. So let me start with a motion diagram. I'm going to use the motion diagram to create our first motion graph. So we're going to pick a very simple motion diagram, one of the ones that I'm pretty sure was on our video yesterday, which is just an object undergoing constant velocity. And we know that it's constant velocity because the magnitude of each of these velocity vectors, these ones that are our changes in position over our 1 second period, are all 2. So I'll do time and position right here. This is time 0, and at time 0, he was at position 0. At time 1, he's at position 2. At time 2, he's at position 4. And you can see that since he's moving forward 2 each time, it's pretty easy to just map this all out. And then it just keeps going, whatever. So I'm going to draw us a quick graph in order to help us draw this all out. Let's see how big it needs to be. That should be plenty large enough. And we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 high. That gets us all the way to the top. And then we'll go, I'll space out the seconds a little bit more just because we have some more space along this axis. 1, 2, 3, 4, 5, 6. So this here is our time axis, and this one here is our position axis. So this is our first type of motion graph. This is a position versus time graph. And I can start mapping this information to this graph. My first position, oops, I meant to change colors there. My first position is 0, 0. Then we can see after 1 second, he was at 2, yep. At 2 seconds, he's at 4. At 3 seconds, we're at 6. At 4 seconds, we'll be at 8. And at 5 seconds, we'll be at 10. So I'm going to draw a line of best fit. I want to emphasize that what I'm drawing here is a line of best fit. While it does happen to connect all the dots, that's because I happen to have perfect dots. But when you're drawing your lines, you want to try and get them as close to all of the lines, but don't play the connect the dot game if it's not possible to put them all in the same line. Okay, so that's our position versus time graph. And it's already starting to give us some information. For example, we can tell by the shape of this graph that it's going in the positive direction. We know that it's going in a positive direction because we can see that as time's passing, he's always more positive than he was before. And so if we look at this graph, anytime that he's going in the positive direction, we will also have a positive slope. And the same thing can be said for the opposite. If we had a negative slope, then we would be going in the negative direction, which is we're going back the way we started towards whatever we defined as our negative direction. And then what else can we tell from this? The last thing we can tell is that if we have a constant slope, that means that we have a constant velocity. And we knew that we had a constant velocity because we already saw that in our motion graph. So a lot of the clues that come from a position versus time graph all come from the slope, and there's a really good reason for that. We know that the slope is equal to rise over run. And if we apply that to this graph, then our rise is our change in position, and our run is our change in time. And as I said in a previous video, change in position over change in time, whether we're talking about vectors or otherwise, is always defined as the velocity. So we can use this slope to figure out what the velocity is going to be in our other motion diagram or motion graphs that we'll do in the next video. So big takeaway that I want you guys to take with you is that you can use the slope of a position versus time graph to figure out what the velocity is. And sometimes you can use it just to find the average velocity, like the average velocity between those points. Or as you get closer and closer, and you use data points that are closer, you can start getting a better estimate for the instantaneous velocity. It's impossible without calculus to get a perfect instantaneous velocity, because that would require 2 points that are infinitely close to each other on the line. But we can get pretty close by just choosing 2 points that have effectively the same slope between them as the slope of the line itself. And we can do that just by eyeballing it. So that's what we need to know about position versus time graphs and an introduction to motion graphs. Thank you for watching.